This is the Atmel SAM E70. It's a Cortex M7 microcontroller which runs at 300 MHz and can absolutely destroy your average Arduino. Compared to the humble Uno, it has a 32-bit architecture, has 60 times more memory, 200 times the RAM, and has all of these lovely features here. Oh, and despite being this powerful, it also runs 18 times faster. So for the fun of it, what if we cram this absolute monster of a microcontroller into the form factor of an Arduino Nano? Did I mention I have absolutely no clue how to do this? Arduino boards like this are designed to be accessible, easy to program, and super intuitive. It's basically designed for children. And unfortunately, a board like this is the limit of my coding skill. I may know a thing or two about hardware, but software is just something I suck at, so that's been my limiting factor for a lot of my projects. Anyways, the point of this project is to finally force myself to learn some advanced code, so I can actually use more complex hardware in the future and break free from Arduino. So I'm at a stage where I don't know how to implement this thing, I don't know how to program it, and I don't even know what coding language it uses. Of course, the first thing I had to do was look through datasheet, after datasheet, after datasheet. I looked at reference designs, application notes, and design guidelines, until I got my first prototype done. So here's my first concept. I did add a bunch of things to this design so that if this chip works first try, I get to have fun with some peripherals. However, none of these will be soldered on until I get this fella working. By the way, adding all of this to my design doesn't actually increase PCB costs. Well, as long as I'm not actually using the components. To be honest, I don't even think I'm going to solder on the USB port or any power management. I want to solder on as little as possible so that if this doesn't work, I don't actually waste too much money. I don't even think I'm going to solder on this crystal oscillator yet, as this chip has an internal clock source as well. But before we solder this, you see how a pin is inexplicably missing? I did this so I can cram a via between these pins. Technically you're not supposed to do this, but I wanted to not have any vias under my BGA chip. So let's say I did want vias under this chip. I would either have to put my vias in my pads, make the vias really small, or both. And these options would like quadruple this board's price. It's actually fairly common to modify a chip's footprint for your own benefit. For example, like this board, the ground pad here actually covered all of this area, but I shrunk it down to squeeze in some traces. Also in this design, I cut the ground pad right in half so I can more conveniently route out this trace. But be careful when doing this though. You should only break the rules once you have a really good idea of what you're doing. Anyways, let's get to soldering. It's probably a good time to mention right now that I've never actually worked with a chip like this before. The most complex chip I've ever soldered was the ATmega2560, you know, from the Arduino Mega, and the most powerful chip I've used was the ESP32S3, but this was just a module, so I guess that's kind of cheating. Ah, shit. Safe to say, this is way out of my comfort zone. Right, so how the hell do I know if this thing works? You know what, let's just plug it in and see if any magic smoke comes out. To program this board, I will be using the MP Lab Snap. So the internet says this works quite well, so hopefully this won't cause any issues for me. Ah, look at that, this also uses the E70. So, bad news, it's not being recognized. I then investigated my schematic really thoroughly, so it turns out I need to connect VDD out to VDD core, and shorting these actually wasn't too bad. All I had to do was to short these two adjacent capacitor pads. So I tried to get this to connect, but no matter what I did, it just wouldn't be recognized. I even tried to reflow the chips with a bit more flux, but still there was no progress. So hi, future Magmabow here. After finishing editing the video, I tried to get these working again, and I actually did manage to get some code on there. But let's go back to past Magmabow, who thought this project was a complete failure. So the answer to can I put an ARM processor on an Arduino is a resounding no. Anyways, thank you for watching. Wait, we can't just give up like that. Even if the E70 didn't work, we could still try again. Hopefully I'll have more luck with an STM32. This microcontroller is bigger, more powerful, and it's got a lot more community support. So theoretically it should be easier to implement. These boards here are about as bare bones as they can get, so we might as well assemble them fully. One thing that sucks about BGA chips is that it's impossible to visually inspect the solder. Instead of a solder being exposed around the edges like with QFN or QFP packages, the solder is entirely invisible under the chip. But on the other hand, soldering these is a bit easier than you might think. These balls under the chip aren't pins like on a CPU, but instead they are actually solder. Since the solder is all pre-portioned, we can just put this chip on our board and heat it up with some flux. So all of the boards in this video were actually ordered from PCBWay, and as always their quality is just perfect. To order your own PCBs, go to PCBWay's website through the link in the description, upload your Gerber files, and place the order. 10 2-layer PCBs that are 100 by 100mm can be ordered for as cheap as $5. So let's quickly talk about this power supply. This chip requires 3.3 volts, but this USB connector can only provide 5, and no power delivery trickery can be used to lower that. So to prevent the voltage from killing this chip, we need to somehow lower it by 1.7 volts. So let's use a simple voltage divider. These three resistors all have the same value, so the voltage at the output should be 3.3 volts. So perfect, we must be done, right? Let's connect something to the output and see if it works. But hold on, it doesn't turn on. Let's measure the voltage again. So you can see there's been a huge voltage drop. This is because this main power path has a lot of resistance, or impedance. So if we connect anything to this output, you can see the voltage drops and we load it down to a level which isn't usable. We can model this microcontroller as another resistor, but you can see its resistance is much lower, so it drags down the overall voltage. So why not compensate for this? Let's adjust this top resistor until the voltage increases back to 3.3 volts. Okay, awesome, now we get 3.3 volts with the microcontroller being installed. Great. Except this actually won't work. Microcontrollers don't use a constant current. So if the load decreases, the voltage goes up and the microcontroller undergoes rapid disassembly. Now let's say the load were to increase. Let's say the microcontroller was doing some complex operation. The supply voltage will drop, the microcontroller will turn off, then because the microcontroller is off, the voltage is going to rise, and then your microcontroller is going to explode. So what can we do about this? Well, voltage regulators exist. They are pretty much just a controlled resistor with some supporting electronics. These are cheap and extremely effective for low power electronics. But let's see what happens with a large load. Well, that can't be good. So because this is essentially a controlled resistor, it gets hot with load, making it inefficient and limiting its current. So what do we do if we do want a high power output? Well, we use a more complicated technique which involves storing energy in coils as magnetic fields and then releasing them back as electricity. This sounds really complex, but it's actually used pretty much everywhere. Essentially, the main component of it is like a transformer, but only with one coil. All we have to do is switch the input on and off really quickly with a MOSFET, and the coil essentially filters out the square wave down to a uniform voltage. This is called a buck converter. Alternatively, we can rearrange the components like this, and then the outputted voltage will be higher than the input. This is called a boost converter. We can even use this sensor PCB to detect these switching fields in real time. So with a circuit like this, we encounter the same problem as with a resistor divider. With each switch, the coil only outputs a constant energy into the circuit. So the voltage will rise with a low load and will drop with a high load. Because of this, there are many buck or boost converter control chips which manage the switching frequency based on a feedback circuit, and this makes the output voltage just right. It's also important to have big capacitors on the outputs of these switching circuits to make sure there's no noise and to give the microcontroller time to react. So why am I waffling on about this? This is because this chip right here is actually a buck converter. It has pretty much everything built in, including the switching circuitry, the negative feedback loop, and the inductor. All we have to do is to add some output capacitors and a small resistor divider. This chip right here efficiently converts the voltage from 5 volts to 3.3 while being able to output substantial current for power-hungry chips like this. Right, so we've got all of our boards assembled now. Hopefully at least one of them works. You know what, let's connect it up and see if anything happens. But before we turn it on, I've just got to confirm one thing. That is, are you subscribed? Wait, what? 92% of you aren't? Well, you'd better subscribe to see more videos like this. And if you've been enjoying the video so far, make sure to like as well. Anyways, let's test these boards. Yes, there we go, it's working. Okay, truth be told, this isn't my first time getting it to work, because the first time was pretty anticlimactic. Now all I had to do was to migrate from the Arduino IDE to the STM32 IDE. As you can see, this is a lot more complicated, so this will definitely take some getting used to. Anyways, thank you for watching. If you've enjoyed the video, give it a like and subscribe. Check out PCBWay in the description, and I suggest you watch this video where I build my own pick and place machine.